Hello world, it's Craig. It's time for an update on this SCMP-based reproduction Digi-Key Nibbler project. So I have the ROM expansion board, got it in, I have it built and tested. It takes a pair of 2732 EEPROMs, so that gives another 2 4K pages of ROM that you can put anywhere you like in the system. And I'll put the build files for all of these boards up on the project page so you can download them and submit them to your favorite board house. I also have the next version of the RAM board built and tested. The changes were fairly minor as I recall. I think there was a silkscreen mistake. But again, this lets you have 2 pages of RAM anywhere in the system. I also have what I'm considering the final version, or at least a long-term version of the Nibbler board itself built and tested. In addition to the little bugs that were in the original, I reworked these jumpers to eliminate the possibility of signal contention when configuring the serial I/O. So now it can be configured to use either the Sense A, like Nibble does, or the processor serial input if you want to use that when you're writing your own code. And the transmit data can be on flag 0 like in Nibble or the serial output. Plus, they can be configured to use the inverters or not so that you either get the normal signal or the inverted signal. And then I also added a reset button up here so it can get a good clean reset even if you're not using the backplane. Now, as usual, there may be a few changes that I make if I ever decide to make another revision, but nothing major, and I don't see that happening anytime soon. Then finally, I have the backplane that I've been using, and that's up on the project side as well. So you'll have something to plug these into if you want to make a system rather than just running the processor as a single board computer. So these are the bare boards. You can download all the build files. It only takes just a couple of minutes to submit these build files to the fab shop, and you can have your own set of boards and then share all the extras. I would encourage you to buy them and then share locally, because I suspect this is going to be the last time we'll be talking about any of this hardware. Now in this video, I'm going to be looking at my resident monitor that allows the Nibbler to do more than just run Nibble Basic. And actually, if it's reassembled with different memory maps, it should run on pretty much any SCMP platform. So what is a resident monitor or a diagnostic monitor? In short, it's a host program that lends the CPU to the user so the user can run their code, but then go back to the resident monitor to get system status or to update things. Resident monitors can be very protective and controlling by playing a supervisory role, but on this platform, there just isn't that much horsepower. So for this, the resident monitor and the user's program simply pass the baton, or token if you will, and whoever has the baton has full control of the system until it's passed back to the other. Neither has more priority or privileges than the other. Anytime the user's code can terminate itself and give control back to the resident monitor, and likewise the resident monitor can pass control back to the user's program. But what the resident monitor does while it has control is to offer a number of tools that help the user build, test, and diagnose their code. Now, I didn't have to write this resident monitor from scratch. When National came out with their development hardware, they had a little 512-byte resident monitor called Kitbug. And it had all of 3 commands. It could spew memory locations to the terminal. It could allow the user to modify the memory contents, and it could switch control over to the user's program. Then recently, Phil G over in the UK took National's Kitbug and really filled it out to make it a capable software development tool by adding another 8 or 10 commands, and he rebranded it as Kitbug Plus, which was well deserving since now it had 4 times more commands and it was now quite useful. Phil's website is a storehouse of knowledge on this scamp, and I'll put a link to his website in the description. If you're looking for Phil's version of Kitbug, you can download it there. And that's the program that I started with. But as great a tool as it is, the problem is that Kitbug, or Phil's Kitbug Plus, won't run on the Nibbler because it relied on a little quirk in the scamp processor. The original Kitbug and Phil's version both require there be coterminous ROM-RAM boundary within the same page. But the Nibbler has all of page 0 filled with ROM, and its 2K of RAM is alone in page 1. The reason Kitbug requires this is because it uses the SCMP's rollover feature, if you can call it a feature, to roll out of the top of a page and back into the bottom of the same page, and vice versa. Remember that with the scamp, when it increments a memory pointer, when it's at the top of the current 4K page, it doesn't increment into the next page. It increments all the way around to the very bottom of the current page. Or if you decrement from the bottom of the page, the pointer comes back in at the top. And this happens if you're just incrementing the program counter, if you're using a displacement jump or a memory reference, doing arithmetic on the pointer, or however that pointer happened to move across the page boundary. It will just roll into the other end of that same page. The way to move a pointer across the page boundary is to explicitly load the page number as the high nibble in the pointer. Anyway, to use this roll around, Kitbug put the stack at the very top of the RAM in the very top of the page. And then whenever the monitor needs to access that stack, or the RAM in general, it can either give a positive displacement to reach up to the stack, or a negative displacement to roll around off the bottom of the page and back into the RAM at the top of the page. It needs to be able to do that during the transfer of the baton between Kitbug and the user's program, and then back again, because that's a critical time for saving and restoring the registers. And it just isn't possible if the processor needs to load the new page into the pointer. It has to be able to use local displacement references that are within the 127-byte distance of the current program counter. As I mentioned, Kitbug and Phil's Kitbug Plus both rely on this little quirk of the scamp to function properly. So I started with Phil's Kitbug Plus that I downloaded from his site, and I reworked the transfer process to make it less hardware specific and no longer tied to this memory mapping limitation. Now, the concept is the same, since the monitor still needs all of the displacements to be local during that transfer process. But rather than rely on a ROM-RAM boundary to be in the same page, I copy a little bit of ROM code up into RAM, which gives the same result. So I have 20 bytes or so that now during the transfer, the main utility can jump into this RAM patch code to start the transfer. And since it's in RAM, all of the references will be local to the other RAM. And then once it's freed up enough registers, the utility can leave that RAM patch code and go back into ROM like normal. And the way it is now, the monitor can be placed anywhere in ROM, or it can even be split. And so all of that, the RAM and ROM locations, can just be specified at assembly time, so you can reassemble this code for whatever platform you've got. Now, once the monitor could run with any memory map, then I went through and I did some enhancements to the existing commands that Phil had put in. So I added some additional features, and I've added a couple more commands to make this Kitbug Plus. So if you're on the fence about building one of these SCMP platforms, I hope to convince you that the toolkits in this diagnostic resident monitor will make it more enjoyable, and you can actually get a lot more out of programming on this scamp platform. The Nibbler, of course, can run National's Nibble Basic, and that's pretty good by itself. But to really get to know the processor, it's my opinion that it needs to be programmed in assembly, and I think a good resident monitor is a critical tool for that. So let me back up a bit into more detail on how a resident monitor works, and it'll become more apparent why the RAM patch step was necessary to save and restore registers. When the user's code terminates and passes control back to the resident monitor, the status of the system is captured and saved. And this is the responsibility of the resident monitor. The user code doesn't have to worry about any of that. And during that transition or the transfer, the monitor takes a snapshot image of all the CPU registers, so the accumulator, the program counter, the status, and so forth. And it saves all of those values into a little patch of RAM that it has reserved. So first, while running in the patch RAM code, it saves the accumulator to RAM, which gives the monitor one working register to use. At some point, it has saved enough registers that the monitor can load the ROM's page address and jump back into ROM to finish the save and transfer process. Once the state of everything has been saved, then the monitor enters its command loop and gives the user a command prompt. Now, while the user's program is idle and the monitor is active, the programmer can use whatever utilities the resident monitor provides to do things to help their program. For example, here's one of the original Kitbug commands, type. And it just spews out the address and the contents. But Phil added a new command called display, which formats the outputs and shows the ASCII representation of the data if it's printable. And then I did some enhancements to this command, like allowing the user to press a space or an enter key to continue the display once that block is done. Now, if something needs to be changed, the modify memory command provides that. And this is another of the original commands. Likewise, with the register command, we can look around and we can take a snapshot of the values of the registers that were taken when the user's program returned control back to the monitor. So these are the registers which Kitbug saved when the user's program exited back into the monitor where we're using it now. And if we want to change a register, we can enter R and the register ID, and then we can change any of the registers that we want them to whatever value we want them to be. Now there's two methods of downloading a program. Either a binary file download where the starting address is given, or an Intel hex file download, which offers error checking and automatically puts the file into the target memory address. Now, there's a copy memory block, and this is very useful if you need to either make a whole copy of something or if you need to move the top part of a program up to make extra space in the code to add instructions. To do a copy, you enter the starting and ending address of the block to copy, and then the destination address. And these can be overlapping. The utility figures out the details of how to copy without destroying data that hasn't been copied yet. Now, this command isn't moving data, it's just taking a block of data and duplicating it somewhere else. Now, if you're using the command to create a space in the middle of a program, the original contents will still be there, which can be confusing. So there's a fill command for that sort of thing, because I find it useful to go back and fill in that hole with zeros or with no ops or something like that. There's an offset calculator to save you from that adding and subtracting that you have to do with that -1 business when you're looking for a new address to jump to. The list command is for program display. With the SCMP, any instruction with a 0 in bit 7 is a single byte instruction. 2-byte instructions have a 1 there. List uses that to format the output as single bytes or 2 bytes on a line. But that only works with instructions. When it gets to the data, the list still follows the same rule, but the 1 and 2 byte per line is meaningless. It's just whatever happened to be in that data. Now, list was a very nice command that Phil added because it makes comparing this file to the list file very convenient. But as nice as that list instruction was, I wanted to also disassemble the instructions back into the mnemonic and the operand. Now, this added about 400 bytes to the command, but I think it makes it much easier to debug the code. And then to complement the list command, which includes the disassembler, I've added a enter command, which also allows the user to enter code in a much more natural way, presuming you feel that assembly language is more natural than machine language. Like many others, we invoke the command and give it the starting address. Here, E6000, which is where I have this expansion RAM board. Now you can enter instructions, and it's going to convert them into machine code. For example, like an LDI 29, XPAH P3, LDI 51, XPAL P3, XPPC P3. So that's just going to load the registers for the iprint command, and the XPPC will transfer the program counter to the iprint. Now, iprint will print out whatever data it finds after that XPPC P3 command. So I also included a pseudo opcode so that you can add ASCII characters. There's a .da, which, like an assembler, allows us to directly insert ASCII characters. So I'll add a hello world message into memory. And we're going to terminate that with an escape. There's also a .db pseudo opcode that lets us put in data bytes in hexadecimal, because the iprint utility requires a 00 terminator in the string. So I'll use the .db. So you notice the .da started with a quote to tell us that it was doing ASCII. .db is going to start with the $sign. So first I'm going to put in a carriage return and a line fee, and then I'm going to put in the 00 terminator that iprint needs. To get out of this, I do the escape again, but This time I have to actually put it in as hex. Now I need to put in the worm start address, so I'm going to do a LDI to 17. Okay, so now we put our program in. Let's go ahead and list that to make sure it's what we want. Into the program, we can also display that. But before we display that, let's look at this last little piece that I put on after the hello world. If we were to run this program without that last message where I reset the P3 to the warm start is how we get back to the monitor. So if we were to run that without that, the iPrint would just continue executing whatever happened to be in memory after this. But I wanted it to return to the debug prompt in the monitor, so I need to set up that P3 and issue the XPPC instruction. If I hadn't messed with P3, it would have still been at the correct value to do a warm start, but I changed it for iPrint. So I needed to go back to the specific warm start address where the monitor will begin saving the registers. So anytime you want your program to return to the monitor, P3 needs to have the correct value and then issue the XPPC P3. So if we display that program, we can see those are our instructions, and then we have the hello world, it's Craig in ASCII, and then we have the terminator, and then we have where we reset the pointer. So now let's go to 6000, run the program, and there's our hello world. Now notice when I list the program, it lists the first part of the program, and then here that where it's in the data, it isn't quite sure what to do with it. It's still interpreting it, that first bit, to see if it's going to do 1 byte or 2 byte, but it really doesn't know what it is. But it's just really coincidence that it got back in sync. You can see that terminator for the iPrint 00, it interpreted as a halt, but then it just, by coincidence, if we were 1 bit off somewhere, it would not have been able to resynchronize, but it happened to resync back in with this LDI and then the XPHP3. Now it's important to put this all in perspective. After adding this disassembly to Phil's list, the size of that list command went up to about 675 bytes of code. Now, in its entirety, National's original Kitbug was only 500 bytes of code, so it's remarkable what they were able to do with such a small code window. In fact, if we look at my help command, which is relatively cryptic, it's 300 bytes. It's more than half as big as the original Kitbug. Now, on this help window while we're here, the command refresher course is nice, but there's 2 very important pieces of information shown here. The first is the RAM that Kitbug reserves for its own use. So we can see the RAM reservation from 1720 to 1769. That's reserved for the Kitbug stack and to save the registers and general working storage. The user's program must respect this reservation or the whole thing comes crashing down. The second is the warm start address. And this is the address that the user's program needs to set the program counter to when it wants to terminate and return back to the monitor. And both of those can be set up or changed when you do the assembly for different platforms. So that's why they're in the help command, because you might need to reference them. And finally, there's a version command. It tells you what version you're working with, because right now this is changing quite frequently. Now let's go back and look at the go command. In the process of handing control back to the user's program, the resident monitor backs itself out and returns the CPU back to where it was when it terminated, except for any changes the user made in the system registers or the memory or whatever, using these utilities in the diagnostic. And then those new values are used when reloading the CPU registers. As I talked about the patch code, that's the second time that the RAM patch code is used. The resident monitor puts the pointers back the way they were, the status and the extension registers, then the accumulator, and finally, when everything else has been restored and there's no trace of ever being interrupted, the resident monitor puts the program counter back to the exact place it was when the program terminated. The CPU fetches the next instruction, and now the system is completely executing the user's code as if the resident monitor weren't there at all. And this all happens seamlessly from the user's perspective. Their only responsibility is to terminate the program in a proper manner so that the processor can find its way back to the resident monitor, and that's what that warm start address is for. As I mentioned earlier, if in the normal course of events, the user's code changes that pointer for its own use, like I did when I wanted to use the iPrint utility, then the code needs to change it back to warm start. Once P3 is set to warm start, then the instruction xppc P3 swaps it with the program counter, and the CPU is now executing a resident monitor code again. Now, this isn't nearly as convenient as setting a breakpoint in something like the 885 or the Z80 or anything like that, but it does get the job done. So with this monitor, with everything that I added, the version can still fit in 4K, so it fits in the 2 EEPROMs on the main Nibbler board or in one of the 2732s on the expansion board. So the source file and a few versions with different memory mapping is on the project page. And if you need a memory map that isn't there, let me know and I can add it to the software package. But the source code is there, and you can easily set the values in the header and reassemble anytime you want. So for the Nibbler, you want the version on the project page, it's called page 0, because that's where these 2 EEPROMs are. And remember, that goes into 2 EEPROMs, the base one starting at 0 and the second one starting at 800, and you'll probably need to put in the offset in your programming software so that it puts the right portion of the hex file into this second EEPROM. Okay, that's it for this video, and as I mentioned earlier, at least for the foreseeable future, that's it for the Nibbler project. Now, this has been an extremely enjoyable project, and I'm glad that I came upon this board. I didn't expect that the Scamp to be my cup of tea, but I've been pleasantly surprised, and I'd wholeheartedly recommend this. Sometimes I get in a rut with projects from my old favorite microprocessor families, but I'm glad I took this adventure. It's a little bit further off the beaten path than just another 8085, Z80, 6800, or 6502 project that I'd normally do. So I think my next project is going to be another processor that's new to me, and it may actually be new to most of you also. So until then, thanks for watching, and I will talk with you later. Bye-bye.